All right, let's talk about some really neat numbers, which are the prime numbers. Prime numbers are super cool, and they are important to us. We see them come up in nature. We use them in our lives all the time. So prime numbers are pretty important, and they're honestly not that hard. So there's something that we can learn, and you probably remember the phrase from a while ago. We just need to refresh your memory on them. Before I get to prime numbers, though, I first need to define one other thing, and those are the natural numbers. The natural numbers are sometimes called the counting numbers because they're what we use to learn to count. Like when you're way back, little itty bitty, and you're first learning to count, the first thing that you learn to count is 1. Right? You don't worry about negatives or decimals, fractions, and that. You just want to count. Your very first counting. 1, 2, 3, 4, 5, and you just keep going. And these natural numbers or counting numbers go on for infinity. So that's why we have this ellipse right here. That dot, dot, dot just means this goes on forever and ever and ever. And then I put it inside of brackets. That's just our notation, like kind of like our grammar, to say this is a set of numbers. So prime numbers, and then we'll talk about composites too. The prime ones are the special ones though. The prime numbers come from these counting numbers. So they are special natural numbers, special counting numbers. So no negatives, decimals, fractions, none of that. Just special types of these natural numbers. Now, prime numbers are numbers where we don't have divisibility. So we need to define that. So divisibility is when one counting number is divisible by another if the operation of dividing the first by the second gives us a remainder of 0. That's just a fancy way of saying when you divide it, we don't see any decimals. We don't want to see any remainders. So like 10 divided by 2 is 5. It comes out nice and pretty. But 11 divided by 2 gives me 5.5. I don't want that. I don't want any of the decimals, no remainders. A little bit of new notation that sometimes comes up. I'll give another example here. We've got this line right here. That means divide. So I could say 3 divides 12. Right? 12 divided by 3 is 4. So we could say 3 divides 12. Now there are lots of different ways that you can define a prime number. There are lots of accepted definitions. So I'm just going to just write up one of these guys. But there are other ones that are all equally as great. So a prime number is a natural number, like we were talking about up above. That way you would know what a natural number is. Greater than 1. So we're not dealing with 1. Like we're starting with 2 here. So a natural number greater than 1 that has only itself and 1 as factors, which means only 1 in itself, only itself and 1 divide their number. So let's look over here. I've got this little nice list of numbers here. If we take the number 2, for instance, I can't think of any 2 numbers besides 1 times 2 that would be factors of 2. For instance, I can for 10. 1 times 10 is 10. They're both factors, but so is 2 times 5. Those are also factors. Prime numbers don't have the other option. They only have the 1 in themselves, no other option. We're going to, so we have some in our idea in our heads, like what some of the prime numbers are. We're going to circle the prime numbers up to 100. And I promise it is not as grueling as it might seem. I'm going to eliminate a whole bunch of them at the beginning. So you see I've got 2 circled here. 2 is prime. It is the smallest prime number. And it happens to be the only even prime number. Every other even natural number is composite. That's because 2 is a factor of all the other even natural numbers. So like 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8. All these other even numbers are not prime because they have factors besides 1 in themselves. So I'm just going to cross them out. None of them can be prime. Remember, I'm supposed to be finding all the prime numbers up to 100, and I'm just saying these guys can't be prime. There's no way. So I'm just going to cross them all out. We don't have a formula to find prime numbers, so we kind of just have to do like this by hand method. We do have computers trained to do this, so we don't have to do it all by hand to find really, really large prime numbers. But we do not have a formula to find them. Is finding the next one's kind of always a mystery, a little bit of a game to it, finding new prime numbers that exist out there. All right, the next prime number is 3. Nothing besides 1 and 3, 1 times 3 gives me 3. Nothing else I can multiply together to give me 3. Well, just like I did with 2, any of the multiples of 3, think about those multiplication tables that you had to memorize in elementary school. All the rest of those multiples can't be prime because 3 is a factor. So for instance, 6, I kind of already crossed that out. 9, 12, 15, 18, 21, the multiples of 3. I'm just going to cross out all the multiples of 3. I know some of them are already crossed out. If you don't want to double cross them out, that's fine. You don't have to double cross them out. I'm not going to be upset at all. So I'm crossing out all the multiples of 3, right? Anything that divides into another number evenly, you can count, is every third one is kind of the pattern to it. So every third one of these is a multiple of 3. Those are all the multiples of 3. Next prime number is 5. 5's easy. It's all the ones that end in 5. 5, 10, 15, 20, 25, 30. If we want to cross these guys out, we can. I know that a lot of them are already crossed out. It doesn't matter if you double cross them out. You can if you want to. Now you might be thinking, oh my goodness, how long do we have to do this? Great news, we don't have to do it that much longer. We have a rule, a theorem, that says you only have to go up to the square root. You only have to check prime numbers up to the square root of our goals, so up to the square root of 100. So we only have to check to 10. So the only other number I need to check is 7. Everything else is already crossed out. So I'm going to do the multiples of 7. Most of the multiples of 7 are already crossed out, everything up to the number 49. And I'm going to do all the multiples of 7. It's okay if you don't remember these. You can do them in your calculator, or you can just count over 7, right? Every 7th one happens to be a multiple of 7, so you could do that. So I'm at 49. 1, 2, 3, 4, 5, 6, 7. There's 1. 1, 2, 3, 4, 5, 6, 7. 7 times 9 is 63. 1, 2, 3, 4, 5, 6. There's 7 times 10. 7 times 11. 1, 2, 3, 4, 5, 6, 7. There's 1. 1, 2, 3, 4, 5, 6. Oops, 7. 1, 2, 3, 4, 5, 6, 7. All right. Everything else that I have left is a prime number. Now, it's a good idea to know some of your prime numbers. We're going to be using them later to do some prime factorizations. I don't think you need to memorize all these guys, but you do need to know some of these smaller prime numbers, these first guys up here, so that when we have to use prime numbers to work some problems, you know what numbers you should be testing for. So it's a good idea to always know some of those prime numbers. Everybody that I crossed out is a composite number. Notice 1's not in my list, so 1's not prime or composite, right? Because both my definitions say a natural number greater than 1. So the ones I've circled up here are prime. The ones crossed out are composite. And there is no largest prime number. Prime numbers go on forever. Like they found huge prime numbers. Like mathematicians have found digits that are 22 million digits long. Like the number 1 written 22 million times. We're finding prime numbers that long, right? So super, super long. And there, like I said, there's no formula for them, but we know we'll never get to a point where there aren't any more. There will always be more prime numbers out there. And it's always fun to see who might find the next one and how big it might be.